Part 2 of Session 6 on the Building Science MoBE Nexus, but one announcement before we start. If anybody lost their Metro card, it was just given to me by David Butler. Thank you, David. And you can come and see me if you've lost your Metro card. Smart trip. All right, so our first speaker is Betsy Pugel from NASA, and she's going to talk to us about tiny houses in space, I guess. So, Betsy?
So good afternoon. I have the unenviable task, I think, of giving the first talk after lunch, but hopefully this will be kind of an addition to your dessert. Again, my name is Betsy Pugel, and I work in the Office of Planetary Protection at NASA headquarters. And our built environment is perhaps a little bit different from, or maybe it has some overlaps with some of the environments that have been talked about over the past 2 days. We worry about tiny houses in the sense that, and I'll talk about this throughout my talk, on the surfaces of spacecraft. So again, I work in the Office of Planetary Protection, and I need to kind of give you guys a little bit of an overview of what our office does and why we exist and where we fit in the scheme of both NASA and in the international community. We'll talk a little bit about the NASA standard assay, so what we do in order to assay spaceflight hardware. So that's everything from spacecraft to the scientific instruments to all the things that are used to put everything together. And then I'll talk a little bit about, and this will just be scratching the surface if you pardon the pun, the last 3 parts of my talk will really deal with material selection as they relate to the development of spacecraft. And so I've broken it down into 3 categories. One is relative size scales, so how the surface roughness interacts and creates little homes in which microbes can live. The actual shape of those little structures that contribute to roughness, whether they're square pegs, round holes, or none of the above. And then I'll talk about material selection in general, so looking at metals and nonmetals, and specifically focusing on some common material classes that we use at NASA, both polymers and metal oxide surfaces. So just a little bit of background. I do love Kang and Kodos from The Simpsons, so you will see a lot of them in here. But planetary protection is an important part of what makes NASA in its development of missions that go out into the solar system. Planetary protection as an office, the missions that our planetary science missions, they're required to comply with specific requirements to protect both the science and the places in which we're exploring. So those requirements vary depending on the mission's objectives. So let me tell you what planetary protection isn't, because we always get these questions. Planetary protection is not Armageddon. We don't have Bruce Willis. We don't worry about asteroids slamming into planet Earth. And we don't worry about those big things like, I think it was yesterday or the day before, actually our sister office, the Planetary Defense Office, tested out an Earth-based system to look for those things. So we are not planetary defense. We don't look at big things. We also don't carry ray guns like the men in black. It's always fun to point out you really did not see anything, but we don't carry ray guns either. But what planetary protection is, and I think this is great for this audience, is we focus on the little things. And so we worry about the same kinds of things that I think all of you worry about and have been talking about over the past day and a half. We limit our focus to heat-shocked organisms, and I'll talk a little bit about that when we talk about the NASA standard assay, but we all have that common ground there where we worry about microbes too. Why do we worry about them? We worry about them because we want to keep open future opportunities for exploration. So as a microbe goes and journeys off, it says, adios Earth, hello solar system. It could end up in a location that could affect future science and affect the ecology of that local planet. So we call that forward contamination. So that's one aspect of planetary protection. The other side of things is when we bring samples back. And so here, Kang and Kodos again, so you got to humor me. When we bring samples back, we want to make sure that the probability of those samples posing a biohazard to us and potentially affecting our civilization, that we take proper steps to have those tests conducted and the awareness there. So that's the backward contamination part of things. And it's not just NASA that develops these requirements and looks at them from this global perspective. It's actually a part of the Outer Space Treaty. So this is a UN treaty that was developed way back in the early days of the dawn of the space race. So that's what planetary protection isn't and is. The central question that we worry about is, what is the chance that a terrestrial organism can potentially influence now a biological investigation later? So I call it the now and later question, to keep it simple. But we concern ourselves with the impact that a terrestrial organism could have on another planetary body, on the future exploration of that body, whether it's robotic or human, if there's human settlements on Mars down the line. That's what we concern ourselves with. And again, NASA has different requirements depending on what the mission's intent is. So if it's orbiting, right, it's a different set of requirements compared to if it's landing or contacting, or if it's going to regions where we know there is a probability for life to potentially exist, life as we know it, we take additional precautions. So it's a kind of varying scale of stringency depending on what the mission does. So just to give you a sense of the scheme of coverage in the solar system, this is an image of the solar system. And the things that are labeled in orange are the things that we worry about from a bioburden tracking perspective. So we worry about Mars, that's an obvious one. We worry about some of the moons around and near Jupiter and Saturn, so Europa, Titan, and Enceladus are the big ones too. And so those are really the ones in which we are hard hitters when it comes to looking at bioburden and tracking bioburden on spacecraft. And so just to repeat that, so we worry primarily for bioburden, and this is where the NASA standard assay comes into play. We worry about Europa, Mars, Enceladus, and Titan primarily for bioburden tracking purposes. And so to give you some background, this is what the NASA standard assay looks like. So we sample some spacecraft hardware, we do both swabs and wipes, and then process it. We do sonication and heat shocking, and heat shocking is really to select out for certain organisms, primarily for bacillus spores is what we're counting at the end of the day. We go through, and I just went through this last week for the Mars 2020 rover, you go through and plate it, check the growth after 72 hours at 32°C, and if it's all clean and dandy, great. If it's not, then we talk about it, and the project goes back and re-cleans the hardware. So it's an in situ process, takes 72 hours. We do also use ATP. I know that one of the previous speakers talked about ATP. We also use that as a kind of rough, in the field kind of a way to assess the level of cleanliness of hardware as well. And so this is what assaying looks like in real life. These are a couple photographs from different missions. On the leftmost corner, this is from the Mars Science Laboratory or Curiosity rover mission. This is actually part of a very large heat shield, which is very, very wide, very large. The interior portion that comes into contact with the rover. This is from the InSight mission, which is a Mars lander. It will launch in 2018 in May on Cinco de Mayo, actually. This mission has solar arrays, and this is assaying the kind of bottom panels of the support structures of a solar array. So if you imagine they're like wings of a butterfly, very, very large wings, we were assaying kind of the underbody of that part. This is part of an exterior of a capsule for the ExoMars mission, which was actually a European mission. The Europeans have a little bit of a difference in their standard assay, but kind of similar process. And then, rover exterior. So this is the tiny Sojourner rover, which was about this big, long time ago in the 1990s, went to the surface of Mars and crawled around there for a while. So lots of different kinds of materials are what you see here, and lots of different kinds of geometries and lots of different surface finishes. And so what I want to talk about next, and this is the bulk of my talk, is a review of the existing literature, and I wrote a paper on this for the engineering community as a whole, because what I discovered in working in planetary protection, which I came to work with Cassie Conley, who's here in the back of our audience, who's the NASA PPO and has been for 10 years, you realize that there's a real difference in the language that the engineering culture and the biology culture uses. And so we started putting together a series of kind of communiques, if you will, to the engineering community. to translate what we know on the biology side in language that is more familiar to the engineering community as a whole. And just as a general note, I'm a physicist by training, so it's great to be in both worlds. So the key parameters that we find influence the tiny housing habitability, if you want to call it that, there are three that I'm going to talk about. One is the surface finish itself. So when you go to select a material, whether it's stainless steel or titanium or some other material, and this is really common for metals, right, there are certain size scales associated with that surface finish, translated into a measurable roughness. The other part is the shape of the surface finish. So are they long rectangular canals, or are they dimpled structures? Are there pits or defects or unique shape features that are a consequence of how the surface is prepared? And then finally, the surface composition itself, whether or not chemically you end up with different surface states that are either hydrophilic or hydrophobic, or what overall is the architecture of the surface energy as a result of composition. So I'll talk about these three things. So the first one is roughness, or whether or not size matters. And there are a lot of papers in the literature out there about this, but really, the simplest one, I think, for everyone to understand, right, is the head of a pin. What can actually grow on the head of a pin? And as you can see, without cleaning it, right, there's a lot on the head of a pin, and the organisms tend to align themselves, right, with the actual mechanical surfaces of the pin itself. But that's not enough. It's important to go through and actually look systematically at what features and size scales can drive different kinds of ordering behaviors. And so what this is it's an engineered, it's an engineered silicon microstructure with variable spacing. So from 1 micron, 10 microns, 0.6, 0.8, and 2. And so they've actually done deep reactive ion etching to generate these structures in silicon, and then looked at both Staph aureus and E. coli to see if there was any kind of difference in adhesion and retention and ordering of those in these micropillars. And so what did they find? They found that size mattered. They looked at a wide range of times in growth and adhesion and found, and this is confocal microscopy, the areas that are dark here are the areas in which there is no response from the labeled organisms. And here is kind of, I think, a better, you get a better sense of where the threshold is for organism size. So this is, as a function of the sizes of the micropillars, there's definitely a threshold that's pretty close to the actual sizes of the organisms. So for Staph aureus, you start to see a drop-off in the growth and adhesion that's close to roughly the size scale of Staph. And then for E. coli, the same for it, closer to about 1.5 microns. And so this is just one of many examples, and I can provide you with lots of different references. They're actually in the paper associated with this that show that the size scales really do end up constraining what the growth is on a given surface. So for this case, right, for these micropillars, they showed that when the periodic spacing is close to the organism size, you see reduced growth. And these are scanning electron micrographs of a similar study, although this is on 316 stainless steel, and stainless steel is one of the really common materials that we use to build hardware. Aluminum and titanium are similar, and there are similar studies to this. But really what you want to see is these are different common surface finishes, everything from very nice and smooth diamond polish to a very rough surface finish, and you can start to see that there are variations in how well populated these surfaces are relative to the surface roughness. And so this is the data to show it. This is just a great series of work. This was the start of many papers that this group had put together. These are different surface finishes here, but the upshot is that as roughness increases, and that's in this direction, the total number of cells increases up to this one specific diamond polished surface, in which case the actual surface chemistry starts to play a role. And so that's the message, at least I want to leave with you for size, is that size does matter. And for most engineers, when they go to build flight hardware, unless there's a real driving case, like an optics driving case or some mated surface driving case where you know that you have to worry about the surfaces themselves, as a whole, the engineering culture at NASA doesn't historically worry about surface finishes. And so what we're trying to do is change that perspective by making it clear that these kinds of surface roughness features literally serve as tiny homes, which you all know well. So size is not the only thing that matters. We also worry about shape. And this is a common picture that I show to engineering folk who marvel at the fact that there is this diversity of shapes that exist in biology, and that these shapes can, in some cases, really move and morph, and that the geometry really does matter. This is one of many examples here as well. This is Pseudomonas aeruginosa, which I know some of you have talked about over the past couple of days. These are also micropillar studies in which they looked at ordering, in which the rod-shaped structures actually go through and order themselves between the micropillars and align themselves in a way, and this is true for a lot of other geometries too, this is just an easy example to put forward, that microorganisms tend to align themselves in ways that maximize their surface area. So it's a surface area to volume ratio kind of method that they somehow naturally find their way. So the third part of my talk really gets to the heart of material selection. And I'm not going to talk so much about metals and nonmetals. I'm going to focus on two non-metal cases, looking at both polymers and looking at metal oxide surfaces. So I talked a little bit about metals earlier, and I think, at least for the purposes of this discussion, the roughness part plays a key part up to certain limits when the surfaces get really smooth. But in the nonmetals, the situation is pretty interesting. So this is there's a lot of stuff going on here. These are all different strains of Staph epidermidis applied to both silicones and acrylics, and these are also really commonly used in NASA missions. Silicones, except for if you have a silicone excluded mission, in which we do have those, silicones are really commonly used. They're on the jackets of wire coverings, like this wire harness here. They're silicone-based compounds that are used to generate seals. There are a wide range of applications at NASA. And so getting people to think about the differences in how a microbe may behave in an environment like a polymer is a kind of new thing for a lot of folks there. So the key thing from this study is that, for the most part, most polymers have these hydrophobic surfaces, so any strain that has a kind of hydrophilic exterior associated with it tends to adhere better. And in this case, you can see that there are strains that adhere more to silicone versus acrylic, and then there are other strains later on in this study that actually show that they have increased adhesion on silicones. So just to bring awareness that not all polymers are the same, not all metals are the same, not all strains of different organisms even can be the same, right? There's a wide diversity and a selectivity that has to come into play when selecting out for different materials when you go to design different pieces of hardware that may be particularly needy and sensitive to microbes. So this is metal oxides. It's a similar kind of argument here where we look at, and these are a wide range. So this is tin on silicon, a whole bunch of silicon states, and really the upshot is there's aluminum oxide, tin oxide, titanium oxides of different kinds, and iron oxides. And the interesting thing is that all these metal oxides show a lot larger number of adhered cells compared to uncoated glass, and in some cases to just the metal itself. Yep, almost there. And so what's interesting about the study too, from my perspective as an aside, is that iron oxides actually show the greatest adhesion. And just from a perspective of looking at what the iron oxide content is on Mars, it makes you wonder what the material selection would be and the microbe interaction would be for adhesion in the Martian environment. And so I just want to leave you with these are the three main parameters that from our perspective, we like to start thinking about at NASA with respect to these tiny houses and their habitability, looking at the tiny details in a given surface. We think more about the surface roughness, the shape, and then the composition and the hydrophobicity. So it might be just a scratch, right? But some call it a home, and that's really the upshot of what I wanted to get across to you today. So in the end game, what we want to do is make sure we keep our solar system weird, and this is our website. So thank you.
I love this presentation. I had mentioned we need research on material transformation. Betsy, you may want to come back here. And this sort of really plays to that. So, time for some questions.
Hi, thank you for including the topic of planetary protection in the MoBE meeting. I was wondering, due to the fact that microbiologists now use more and more molecular methods, if NASA should also care about biological molecules, so maybe methods to mask them with PMA on a mission, so on a spacecraft, before that they are not jeopardizing a life detection mission.
Yeah, so what I didn't talk about, just given the time constraints, is there's a lot of work that our office invests in molecular methods and metagenomics, and so I didn't get into that here, but we don't just do the NASA standard assay, so there are a lot of other techniques we do as well.
Okay. So is there the chance that it will be extended to other methods than the standard assay in the future?
So the standard assay, and Cassie, I don't know if you're still here, there are different techniques that we do use, right? The requirements where they are right now, right, are strictly for the NASA standard assay. But, we are always open, and we are constantly evolving with respect to how we evaluate things and even how we sterilize things. So we don't just do dry heat microbial reduction anymore, right? We do vapor hydrogen peroxide, and we investing in doing other techniques too. So it's just establishing a solid ground from a verification point of view so that you can say, straightforwardly that what we see is what we see.
Okay, thank you.
Yep.
I'm wondering why specifically 316 stainless steel and then perhaps what about copper?
Yeah, so 316 it was just a great example for the sake of this talk. I mean, we use a lot of different kinds of stainless steel, not just 316 is pretty rare, actually. We tend to use it for heat pipes, but it's a good example, given a lot of the discussion that we've had too about plumbing and tubing, which is why I brought it up here. Copper tends to be used primarily for like conductive planes for electrical purposes, so it's definitely there. It's just not necessarily the go-to for the larger mechanically stressy pieces, the things that really have to bear the load for launch and landing.
Because I've seen publications that they have certain antimicrobial effects.
Yeah, so there's a whole part in the paper that I wrote associated with it that gets to antimicrobial properties of copper and gold and silver and the diversity of applications that could exist. So yeah, you're right on.
Thanks.
Yep.